Hello, in this video I'd like to talk about the expressive power of full arithmetic. So the first order logic of the natural numbers with addition and multiplication. With just addition alone, we could talk about numbers being even or odd, whether they were of the form x plus x or x plus x plus 1. Or we could talk about their remainders modulo any fixed number, modulo 3, modulo 4, modulo 5, whatever, as long as it was a concrete number. But we couldn't talk about remainders modulo some number that was given by a variable. If we're talking about the first order logic of the natural numbers with addition and multiplication, however, we can very easily talk about remainders modulo arbitrary variables. So we say that z is the remainder when x is divided by y if there is some k such that x is equal to k times y plus z, and z is the smallest such z. So specifically, there is not a z prime that also makes this true for some z prime that's strictly less than z. And remember that we can talk about less than or equal to because we have addition of natural numbers. As previously, we can take this remainder function and use it in larger expressions by taking those larger expressions and relationalizing them, breaking them apart into a bunch of separate formulas, and one of those formulas is going to look like the remainder when x is divided by y is equal to z, and then whatever we wanted to say about the remainder when x is divided by y, we will say about z instead, and we'll say that there exists a z that makes this true. Having this remainder function allows us to construct a key piece of the proof of Gödel's Incompleteness theorem, and that's Gödel's beta function. Gödel's beta function takes in three inputs, a, b, and c, and returns the remainder when a is divided by 1 plus c plus 1 times b. The key property of this function is that it allows us to encode arbitrary tuples of integers given just two numbers. So given any sequence of natural numbers x0 through xn, we can find two natural numbers a and b that together encode the sequence, where beta of abi is equal to xi. And maybe we want to have an extra variable n to indicate the length of this thing, because of course we can plug in values into this third component here that are larger than n, and then we're just going to get garbage data back. We could at this point go a step further and actually have one natural number encode these three natural numbers that encode the sequence, but that isn't such a big deal. When it comes to first order logic, there's actually not that much of a difference between saying that there exists a c that encodes an a, b, and n that have certain properties, as saying there exists an a, there exists a b, and there exists an n having certain properties. The difference between quantifying over one variable and quantifying over three variables, not that big a deal. On the other hand, first order logic does not come with a built-in way of quantifying over arbitrary tuples of elements of our structure. If we wanted to be able to say there exists an x0, x1 through xn satisfying some certain properties, we would need to translate it somehow. And having the ability to talk about arbitrary sequences with only three variables allows us to translate this sort of notation, which isn't valid first order logic, into there exists an a, there exists a b, and there exists an n satisfying certain properties, and this is valid first order logic. So being able to do this sort of encoding gives us a new expressive power that we didn't realize that we have before. Let's talk about a proof of this fact. We start our proof by letting b be a large factorial. Essentially just take all of the numbers that show up in the problem, take their maximum, and take the factorial of that, and that should work. Then I claim that the numbers that show up here are going to wind up being relatively prime to each other for the various values of I. Why is that? Well, suppose that we have a common prime factor of two of these terms. then p is also going to divide the difference between these two terms. First, note that p cannot divide b, because if p divided b, then p would divide evenly into I plus 1 times b. But we said that p divides evenly into 1 plus that, so that means that p cannot divide b. I minus j is going to be at most n, and by picking b to be larger than n factorial, we know that I minus j is going to divide evenly into b. And so, because p doesn't divide into b, but I minus j does divide into b, then p also can't divide into I minus j, because then it would, by transitivity, divide into b. So this is a contradiction. We can't have a common prime factor of two of these terms. So what we've done is we've proved that there is an arithmetic sequence of numbers which are relatively prime to each other. This sets us up exactly to use the Chinese Remainder Theorem, which says that there is some a whose remainder modulo these various moduli is going to be equal to whatever numbers we want them to be, assuming, you have to assume that this number is at least xi, but you can do that just by ensuring that b is large enough. But this is exactly the statement of the Chinese Remainder Theorem. If you have relatively prime moduli, and you have some things that you would like a number to be congruent to, modulo those moduli, then you can find a number that has those congruences. And this is it. Note that b is going to be pretty large. It's going to be the factorial of the numbers appearing in the problem, and that a is going to be quite a bit larger. Here are some actual encodings of actual sequences constructed in this method. Having access to this beta function allows us to express arbitrary recursion in our logic. So for instance, we can say that p is equal to q to the r if there's some sequence encoded by a and b such that the 0th element of that sequence is 1. For each element of the sequence, the I plus first element of the sequence is q times the ith element of the sequence, and p is the rth element of the sequence. And of course, if you wanted to do some other sort of recursion, you could just replace this q times by whatever function you can describe in this particular logic, applied to beta of abi. We can even encode two-dimensional arrays of natural numbers. So suppose that we have a two-dimensional array. We can encode the first row with a suitable a and b. We can encode the second row with a suitable a and b, the third row, and so on and so forth. And then we just have tuples of a's and tuples of b's, which we can encode as a pair of numbers. So we'll let c and d encode the tuple a0 through an, and we'll let e and f encode the tuple b0 through bn. And then we can index the element at position ij in our array with the formula beta of beta cdi beta ef ij. This lookup will tell us what ai is. This lookup will tell us what bi is. And then looking the jth element up in that will tell us what the jth element is of the ith row. So by having a c, d, e, and f, and of course m and n encoding the width and height of this two-dimensional array, we can encode arbitrary two-dimensional arrays of natural numbers. And at this point, if you're familiar with Lisp, you might be saying, oh, we have recursion, and we have the ability to talk about lists of lists, and you could keep going with this process here. You can talk about lists of lists of lists, and so on and so forth. This should be Turing complete at this point. Of course, back when Gödel first proved his incompleteness theorem, he didn't have access to all of this machinery that we have nowadays. He couldn't say, oh, I obviously have Lisp, Or eventually we'll get to the point where we obviously have Turing machines and then say, oh, well, of course Turing machines can reason about proofs. He didn't have that machinery. And so it's actually really interesting to go back and look at Gödel's original paper, because he's essentially trying to program in this first order logic. He's trying to write a computer program prior to the invention of the computer that recognizes valid proofs, essentially encoding logical formulas as lists of numbers and then using prime powers to encode that as a single number, and then showing that using this recursion, you can reason about these formulas in a reasonable way. So let's take a moment to go into the detail of how we can construct formulas that correspond to Turing machines using our ability to describe two-dimensional arrays of natural numbers. I find it really helpful sometimes to think of Turing machines as a one-dimensional cellular automaton. You may have already heard of the two-dimensional cellular automaton, Conway's game of life. So the rule for cellular automata is this. It takes place on a grid, and the configuration of any cell on that grid at time t depends on the configuration of the neighborhood of that cell at time t minus 1. So when I say neighborhood, I mean the cell itself at time t minus 1, its previous configuration, and the previous configurations of all of the cells neighboring it. If we have a Turing machine like this, we can modify it so that everything is taking place within the cells simply by including the head as part of the cell that it's currently pointing to. In other words, we will modify the set of characters that can appear in each cell so that it is the set containing all of the original characters of the alphabet, and then all symbols of the form some state of the Turing machine, and then a little arrow symbol to indicate that the head is there, and then some character of the original alphabet. This is still a finite collection of characters, and the character that's going to wind up in each cell at time t depends exclusively on the characters that wind up in that cell and its neighbors at time t minus 1. In particular, usually it's going to be the case that the character, we know at the next time step for the operation of this Turing machine that this character is going to stay the same, and this character is going to stay the same. The only thing that could change are the characters nearby the head. If the head is going to move or write to the tape, this cell is going to change according to the rules of the Turing machine, and depending on which way the head is going to move, it might wind up being the case that this cell gets replaced by one of our more advanced the head is here symbols, or this cell winds up getting replaced by a more advanced the head is here symbol. But whether that happens depends exclusively on the current state of the head and the character that it's looking at, which is information that is accessible to these three cells in determining where to go next, what to become next. It's very common to represent runs of one-dimensional cellular automata as two-dimensional arrays, where each row represents the configuration of the automaton at one particular time, and then the configuration at the next time, and the configuration at the next time, and so on and so forth. Typically, these configurations are infinite, both in the spatial dimensions and the time dimension. But if we're talking about a Turing machine having an accepting run, then we're only using a finite amount of space and a finite amount of time in doing that computation. It's only when the Turing machine doesn't halt that it winds up using infinite amounts of our tape and infinite amounts of our time. So if we want to express our Turing machine as a formula in our logic, we are going to say that there exists a CD, E, and F, CD encoding our array of A's, EF encoding our arrays of B's, so that CDEF together encodes our entire two-dimensional array of natural numbers that's going to represent the run of our Turing machine. M and N are going to encode the width and the height of this run. Since there are only finitely many characters that we were using in our extended alphabet for our one-dimensional cellular automaton, each cell, each element of our grid is going to be some number from 0 to the number of characters that we had. And we're going to require that xij, xi minus 1j minus 1, xi minus 1j, and xi minus 1j plus 1, these numbers here, so the number that goes in a particular cell and the numbers that go in that cell and its neighbors at time I minus 1 are all going to fall into a valid configuration. And since there are only a finite number of allowed configurations here, we can just write this out as a really long formula with ands and ors in it. So this will express the existence of a grid whose first row is the starting configuration for our Turing machine, and each row afterwards follows according to the rules of our Turing machine. It's not going to use past this point on the Turing machine tape. And then this last row, we simply have to say that this is an accepting configuration of the Turing machine, that the cell that contains the head is one of those that has a configuration that winds up accepting when it gets read. And this completes our proof. The natural numbers with addition and multiplication are capable of expressing Turing machines. And therefore, by what we did in the previous video, it's going to be the case that there's no complete recursively enumerable axiomatization for the natural numbers with addition and multiplication. And it turns out that you need very little to make this proof work. The biggest thing that we used was the Chinese Remainder Theorem. So we don't need a very robust partial axiomatization, such as piano arithmetic. We can actually work with a much smaller axiomatization as long as it gets us the Chinese Remainder Theorem, which was the key part of this proof. So we can actually use Robinson arithmetic, which remarkably has only finitely many axioms, in order to prove Gödel's incompleteness theorem, in order to be able to construct these Turing machines or reason arbitrarily about proofs. It's also worth quickly mentioning Gödel's second incompleteness theorem here. It requires a stronger axiom system, so let's just say we're talking about piano arithmetic for the moment. It says that if piano arithmetic is consistent, then so we know that there are things that piano arithmetic can't prove, provided it's consistent. If it's inconsistent, then it can prove everything. But provided it's consistent, because piano arithmetic has a recursively enumerable axiomatization, that's how it's constructed. It's constructed as a recursively enumerable set of axioms. We know that there are things that it can't prove. But what are those things? Well, one of those things happens to be the consistency of piano arithmetic. Now, personally, I don't recommend going around asking proof systems whether or not they're consistent, because, well, if a proof system is inconsistent, it will tell you that everything is true. I guess provided it has the principle of explosion. But an inconsistent proof system will tell you, yes, it's consistent. It will also tell you, yes, it's inconsistent. If you ask it any question, it will say yes, and here's a proof, because it's inconsistent, because there's a proof of everything. But the result of Gödel's second incompleteness theorem was particularly devastating because it also meant that there wasn't a simpler proof of the consistency of piano arithmetic. The goal was that we could start with a system that's like obviously true and then use that to prove the consistency of a slightly larger system and use that to prove the consistency of a slightly larger system and work our way up to prove that all of mathematics was consistent. But the situation actually winds up being more like the reverse. If we want a proof that a system is consistent, we don't look down, we look up. So, for instance, if we look at the axioms of set theory, they actually prove that piano arithmetic is consistent. However, is this an indication that we should trust piano arithmetic more, or rather an indication that we should trust ZF set theory less? Ultimately, all of mathematics rests upon the foundational hope that these various axiom systems that we use nowadays are consistent. And it's rather telling that a field of study that prides itself on its certainty has at its core this fundamental uncertainty to it. This fundamental assumption that we have no way of knowing if it's true or false. At this point, it's easy to get sidetracked into a bunch of really interesting mathematical philosophy, but I'd like to keep this video series focused on the mathematics. Just know that I appreciate working at a slightly lower level of consistency strength, where if something broke within mathematics, there's a chance that Buki arithmetic would be spared, that the whatever contradictions we had discovered would not apply in this lower level case. And also I appreciate that the basic questions that we can ask within Buki arithmetic and similar structures are all decidable. Whereas you might be asking a basic arithmetic problem or something similar in some other field, and it turns out that this really basic question is undecidable, that it's somehow encoding the behavior of a Turing machine. The undecidability of the full first-order logic of arithmetic can be used to show that a number of other problems are also undecidable. And in the next video, I'd like to talk about a few other structures that extend the structures that we've looked at before, where their first-order logics wind up also being undecidable because they secretly encode arithmetic. So let me know in the comments if you have any questions about this video, and I hope to see you then.